Assalamualaikum warahmatullahi wabarakatuh. And hi, my name is Nasrullah bin Shukri. Today our group will be presenting about control chart, which is our topic is Xbar and S chart. So my group is uh, me is Mohd Nasrullah, Nuqman Hafiy, and also Yuvanesh Vasu. Hi. So the main contents for our presentation is the introduction. Also, what is control chart and a little bit explanation about X bar chart and also S chart. Hi guys, so for introduction, there are two types of process data. As you can see here, the two main type of process data is variable and also attribute. What is variable? Variable is continuous data, things we can measure. These, for instance, include length, weight, time, temperature, diameter, and so on. So what bar or chart can we use for this type of data, process data, is S bar, R chart, S bar, and sigma chart, and also for the individual units. For attributes, so what is attribute? Attribute is non-continuous data, things we can count. This includes number of percent defective items in a lot, or number of defects item, number of defects per item. So what chart can we use for this type of data is P chart, NP chart, C chart, and also U chart. Hi guys. So what is control chart? Control chart is a graph that shows how a process changes over time. The data shown in order of time. The control chart always has a middle line for the average, an upper line for the upper control limit, and a lower line for the lower control limit. Data from the past is used to figure out these lines. By comparing the current data to these lines, you can figure out if the process variation is consistent or it is random, affected by special cause of variation. Control chart also can be used to keep an eye for a process to see if it's a statistical control, to evaluate a process and figure out its normal statistical control parameters. This is also to find places where a process could be improved. Control chart can be used to keep an eye on both variables that change over time and those that don't. Continuous variables include things like average, dimension, weight, and also temperature. This kind of variables dimension can be calculated over continuous range. Attributes are not quantifiable by nature, but they can be counted, such as the number of broken parts or the number of problem unit inspected. So, the control chart we were going to talk about in this presentation is a combination of the X bar chart and also S chart. This is used to keep an eye on process with continuous variables.
Hi, I'm Yuvanesh. I'll be continuing on what is a control chart. Control charts can be segregated into Short control charts and other control charts. Short control chart, which is predominantly named after Walter Sheward from Bell Telephone and Western Electric, which monitors that a process variable remains on target and within given upper and lower limits. It is a monitoring chart for location which answers the question whether the variable's location is stable over time. And then we have the other control charts, which then range from X chart, P charts, NP charts, C charts, to U charts, MR charts, individual MR charts, and custom data control charts. And the Sheward control charts in particular can then be further segregated into variables and attributes. One might wonder what a variable and attribute is. A variable control chart is used for measuring data, most often in decimal places, and attribute control charts are for counted data, which then includes integers. And the difference between the variable and attribute control charts is that it is used to monitor continuous characteristics of products, while attribute control charts are applied to monitor the quality characteristics, which are not possible to be expressed in a numerical state. And variables and attributes can then be segregated into three each, which are X chart, R chart, S chart, and P chart and C chart respectively for variables and attributes. Hi there. Following that, we'll now be looking at the X bar chart and the S chart. The X bar chart shows how the mean or average changes over time, whereas the S chart is then used to monitor the variation of a process based on the samples taken from the process at given times, hours, shifts, days, weeks, etc. The measurements are of the samples at a given time constitute a subgroup. Most of the time, the X and S charts are used together because they show different but related kinds of information about a process. The X chart shows the central tendency of the data, which is the tendency to of our measurements to cluster in a normal way around an average value or x bar. Even though this is an important number to know and understand, it is also important to know how much of a number varies from its average. The S chart measures and keeps track of variation by recording the standard deviation from the average value in a given sample. Together, the X and S charts can show how stable a process or system is. For example, a sample of 5 measurements might have an average value X of 100 and the standard deviation S of 10, while another sample of 5 measurements might have an average value X of 100 and a standard deviation S of 30. Even though both samples have the same average value, the sample S equals to 30 may be fine, but in others, it shows that it possesses a lot of variation. In some processes, these small changes within the larger control limits may be fine, but in others, this kind of change may not be what you want. In some situations, like when making high-tech products or part of machines, there isn't much room for error. Using X and S charts to track these kinds of processes can be helpful. And as we can see with the formula presented above, we are able to then denote the standard deviation, the means, and also the corresponding values. Hey guys, now we'll be looking at control limits. What are control limits? Control limits are the horizontal lines in a control chart that delineate the upper and lower limits of the acceptable range of a result for a process. When plotted data exceeds a control limit, it indicates that the process is out of control and requires management attention. And how do you find control limits? Control limits are calculated by estimating the standard deviation of the sample data, multiplying that number by 3, adding the multiplied standard deviation to the average for the upper control limit, while subtracting the multiplied standard deviation from the average for the lower control limit. And in six sigma, control limit is where the limits of expected variation of either individual data or sample subgroup data, typically acceptable limits of variation, equates to what one would expect to see in a random process. And there is a major difference between control limits and specification limits. Control limits is more based on the voice of the process, whereas specification limits is based more on the voice of the customer. And control limit is calculated from data, which shows that is based from the amount of data that we collect, and whereas specification limits is defined by their customers. And then control limit appears on control charts, basically the whole topic that we are talking for today, whereas specification limit appears on histograms. And as we can see, when mean and standard deviation of the population from which samples are taken are given, we can then calculate the control limit, the upper control limit, and lower control limit as shown in the formula given in the diagram.
As for my part, I will now explain on how to calculate the S bar chart and S chart and how to uh, obtain the result. Most of the time, only small sample sizes are available because the process capital or label that use S, X, and S charts are expensive, as with most statistical analysis. It's best to have a larger sample size, but that's not a must in this case, since the sample size N will be set to 5 and the sample taken K will be set to 10. This will make things easier to understand and show. In other words, there will be 5 observations in each of the 10 samples. The observations are written down, and for each sample, the average value, which is X bar, and standard deviation are calculated. All of the samples averages and standard deviation are also given average values for the S and S bars. The measurement and calculation that come out of this can be written down in a grid like the table 1 here, where we obtain the average S bar as 0.016 and the average of the S is 0.002. And now we go on how to calculate the upper and lower control limits. The average S bar and average S value are used as the center line or reference points on each chart. The average values from each sample are plotted against this center line. Calculating the top and bottom control limits for both the X and S chart is the last step before setting up the control chart. The S chart is used to figure out the first set of control limits. These are calculated before the X control limits for two reasons. First, to see if the process is statically under control in terms of variation, and second, to find out why the process is out of control. Once the process has been stabilized in terms of variation, the X chart can be made. So the formula for figuring out the control limits for each chart are found by going through a long statistical proof that is based on the central limit theorem, as was mentioned earlier. The proof shows that statistical constants that are calculated based on the number of observations in each sample can be used instead of more complicated formulas to find the upper control limit LUCL and the lower control limit LCL. You don't talk about the statistical proofs and equation here because this documentation focuses more on how the theory is used than on the details of the theory itself. So now we go on the how to calculate the upper control limits and lower control limits for both X bar chart and X bar chart. For the upper control limits for the S charts, we use UCL equal to B4, the constant we gain from the table 2, multiply with the S bar chart as average, which is a value we gain from the table 1. And the same formula also used to calculate the lower control limits for the S charts, which is equal to B3, the constant value we gain from the table 2, multiply with the S bar charts, the average value we get from the table 1. So here we can calculate that upper control limits 2.089 multiplied by 0.002, we get 0.0418 for the upper control limits, and for the lower control limits we get 0.03 multiplied by 0.002, we get 0.00006. So we gain the upper control limit and lower control limit for the S charts. So as the previously stated, of the control values for the S charts are calculated, the control values for the S bar chart are determined using the following equation, which is the upper control limits equal to S bar plus by A3 multiplied by S average. So we get the upper control limits of the S bar charts. And for the lower control limits S bar charts, uh, we use a different formula, which is S bar minus by A3 multiplied by S average. Again, using the values calculated in table 1 and the constant table 2, the following S bar chart control limits can be calculated, which is UCL equal to 0.016 plus in the bracket 1.47 multiplied by 0.02, we get 0.0189 for the upper control limits. And for the lower control limits, we get 0.016 minus in the bracket 1.47 multiplied by 0.002, we get 0.0131. So we get the upper control limit and lower control limits of the S-bar charts with the centerline values in upper control limits and lower control limits all calculated. The S-bar and S-charts can be constructed and plotted, and simple values can be plotted also. So after we gain the value of the upper control limit and lower control limit of both S bar and S charts, we now can put uh, the point in the chart to determine whether it is in control or out of control. Typically, the construction of the S-bar chart and S-chart is done together so that the plotted values can be compared at even intervals. Below, the two charts are illustrated in the figure 1 and 2. For the S-bar chart, we can see that the uh, plotted point in between the upper control limit and lower control limit, so we can see that it is in control. While for the S-bar chart, is also the plotted point also in between the upper control limit and lower control limits, so it is also in control. So here are another example of the chart where we gain the control limits is 14.11 and the upper control limits is 15.37 and the lower control limits is 13.45, where the point is beyond the upper control limits and lower control limits, so the process average is out of control. So for the S charts here, the example here shows that the points are all in between the upper control limit and lower control limit, so we can say that the process variability is in control.